Welcome everyone. Hi, my name is Navina. I'm an engineer at StarTree, and today I'm going to talk about gently down the stream with Apache Pinot. So in this talk, I want to cover and show you how real-time ingestion works with Pinot, and also show you some of the really powerful features in the real-time engine that you can leverage to simplify your data pipeline. All right, so let's get started. So before we dive in, let's understand why we want real-time analytics. So analytics itself helps you make better decisions by giving you a lot of insights into your data, right? So you have a bunch of events that give you insight, and the main thing here is that with these insights, you need to be able to take action that can be very critical to your business application. So real-time analytics reduces this time that it takes to go from events to insights to action. Because if you look at the value of data, a single data, it kind of decays very quickly over time. And real-time fits in this scope, right? It's just as soon as the event happens, you want to be able to process the event and derive any value out of it. You need to do it right away. So this is a spectrum where real-time analytics works. Let's look at some examples, right? So one popular one is LinkedIn's Who Viewed My Profile, right? So this is a dashboard which shows you how many people have looked at your profile in a given window of time. It gives you various other statistics around profile views. And if you look at the dashboard itself, it seems simple, but then if you look at the queries, the number of users itself is like 700 million plus in LinkedIn. And for each, if you scale at that level, then the amount of QPS you get to this, to show this dashboard is in the order of thousands, right? And the latency also needs to be really low. Like it's in the order of milliseconds, because otherwise you wouldn't want to look at a dashboard that's just spinning wheel, right? And data needs to be as fresh as possible. So this is one of the very first use cases at LinkedIn. So let's take a look at another use case at Uber. So Uber Eats provides users, restaurant owners, with this dashboard. And this dashboard provides a lot of metrics on their orders, right? So every restaurant gets a lot of orders. So you see like what is your current sales in real time, how many orders you've missed, and then you can also look at like what are the top selling items. So while this is just a dashboard, right, what this gives the business owner is that they look at this data in real time and they're able to take action right away. For example, if they see like there are a lot of missed orders, then the owner could decide like, okay, you know what, because of a lot of missed orders, we're going to give some vouchers to certain users. So they can take these actions in real time that kind of derives more value to their users. So even for this dashboard, if you look at the scale at which it operates, it is the QPS is in the order of hundreds of queries per second, but the latency is still pretty low. So it needs to be like less than 100 milliseconds, and more importantly, the data has to be really fresh. So you cannot have your data sit somewhere and then look like an hour later and then show this to the restaurant owner, because then they cannot take immediate action. So that's where the real-time value proposition comes in. So this is typically the characteristic of a real-time analytics platform. So you need to have really low latency on queries, and you want to have very fresh data available as soon as the event happens, and the QPS is on the order of thousands. So not only these, but this system also needs to be able to scale, be highly available to requests, and also cost effective. Now the nature of data coming into real-time analytics platform itself is real-time, of course. But then it could also be potentially having a lot more dimensions than a regular data event. And the velocity is pretty high. So we all know that to deal with such high volume, high velocity data, we have systems like Kafka, Kinesis that can clearly transport events at this scale and also be cost effective. Now to be able to query those events effectively with low latency at a very high QPS, this is where systems like Pinot fit in, right? So Pinot helps provide really quick insights into your data as soon as the data becomes available. So given these requirements, I want to first dive into how you go from stream, how you take your data from stream, and how you go into Pinot. So typically if you look, there are a lot of these streaming systems that you have like Kafka, Kinesis, Pulsar, and PubSub. Before you enter into Pinot or any other OLAP system, you typically want to do some kind of processing or transformation, because the events that occur in real time are not really well suited or in the right format to be able to give you a really effective and quick query performance, right? So typically you would see things like data transformations, or you're trying to derive a new data from your raw data, or you're dealing with complex types, or you're trying to modify the data granularity. Like if you take IoT example, the data is too granular for maybe like some of the use cases you're trying to look at, which is only at like hourly or a daily scale, but your data may be at like every millisecond. So you don't want to dump everything into your OLAP store, because then at the end, when you run the analytical query, you will be trying to scan all the data when really you need like an aggregated view. So that's the data granularity part of it. So you would do all these kind of operations with systems like Flink or maybe Spark streaming, and after processing, you again generate an output stream that gets into Pinot, right? So these are simple data transformation or sort of stateless operations that you would do. But there are also like stateful things that kind of work around data semantics. So I'm going to talk about data semantics a little later and in depth to understand what I mean by data semantics. But basically what I'm saying is sometimes the raw data itself doesn't mean anything until you look at relative to a previous event, right? So that is like you're deriving a meaning that needs to go into your OLAP system rather than the raw event itself. We'll look at an example later on in the slide. And there can also be cases where you have multiple data sources and you're trying to bring it into one system, or you want to partition your data differently from how it is in your source. So these are typically like the broad categories of areas where you would introduce a stream processing system to be able to convert your data like raw events into an OLAP compatible events, right? But running these stream processing pipelines is definitely a lot of overhead. And if you're thinking Lambda architecture, then you have even duplication of pipelines, right? You maintain one in the offline flow and one in real time. So that is a lot of overhead. And going forward, I want to show you how Pinot tries to simplify all these operations and kind of keep your data pipeline as simple as possible. So let's get started. And we'll take a look at how real-time ingestion works in Pinot before looking at some examples and features. So real-time ingestion in Pinot, the basic architecture is that it is a partitioned and replicated consumption model. And Pinot creates data and stores it in a distributed format in small chunks called segments, right? So these segments get created periodically based on the events ingested. And as soon as the data is ingested into Pinot, it is available for query. So let's take a look at it. So data itself in a Pinot table is organized as data segments. And these data segments are the ones that hold the data for every single column. So Pinot is a columnar database, so every single column has its own indexes as well. So data segments hold these data values. Now let's take an example where you have like a Kafka topic and 3 Pinot servers. So when you create a Pinot table that consumes from Kafka with 3 topics, the controller basically identifies that, okay, there are 3 topics in my source, and it's going to assign 3 segments, 1 segment per partition. And each of these segments are also replicated across these servers. So all of these servers, as soon as they get assigned a segment, they start consuming from the source. And the minute they start consuming, data starts becoming available, it is also available for query from the brokers. So it doesn't have to wait for the segment to complete to be able to query. You will be able to query it as soon as the data arrives. And periodically, these replicas for every partition will try to seal the segment or make it immutable and push it down to deep store. So deep store is a place, basically like a data backup, where you're trying to keep making the data more durable and available, even if the server crashes, right? So once these sealed segments are uploaded to the deep store, the servers notify the controller through a commit protocol saying like this segment is complete, and then the controller goes and creates another set of consuming segments for those partitions across these servers. So now the servers are hosting both completed immutable segments and also consuming segments at the same time. And all of these segments should be queryable from the brokers. So if you notice, the server itself is consuming, indexing, and also serving results. So let's take a look at how it happens inside the server. So let's take a peek into the real-time engine in the Pinot server. So this kind of summarizes what real-time engine does. It's a very pluggable design, as you will see, and it has a couple of components like the stream consumer. Then there's a message processor which does decoding, transformation, and indexing. And we also have like upsert metadata manager, which handles upsert semantics with the data, and a segment completion handler. The segment completion handler basically is coordinating with the controller to kind of seal your segments, upload it, and then successfully change the segment, start consuming the new segments, things like that. So if you take a look at the individual components, right, every single component is actually pluggable in Pinot. So you have a stream consumer which can consume from any of the popular, you name it, you have a connector for it. So it fetches from a given data source, and that's pretty much what it does. And today we have support for Apache Kafka, Amazon Kinesis, and Apache Pulsar out of the box in Pinot. And StarTree also supports consuming from Google PubSub. So the only requirements for consuming from a source is that you need to be able to apply, either the source is partitioned by itself, or you need to be able to apply some way of defining the partitions on the source. I'm not sure what's going on here. Okay, let me do this. All right. All right, so the next step is once you got your data, it's all bytes. Now you want to be able to decode it and make it into a Pinot row, right? So just like every other database system has its own row format, Pinot has its row format too. Now this is also pluggable. So you kind of deserialize your data and make it into a Pinot row. And out of the box, I think we support CSV, JSON, Avro, protobuf, and I'm fairly certain I'm missing a couple of them. And StarTree introduced a specific decoder called Debezium decoder, and I'm going to talk in detail about this later on, right? So once the data becomes ready into a format that's like a Pinot row, you want to be able to apply some transformation functions. Now the raw events are not, I would say it's very rarely ingested directly into OLAP systems because they're never ready to be in that optimal form. So you will do a lot of transform functions. So common things are like filtering, where you want to not consume all the data, but you want to drop some of the events. Or maybe you may want to flatten your records because you have like multiple levels of nesting. Or you may want to aggregate your data, right? So these are some common transform operations. And once these operations are done, the data itself is ready to be indexed in memory, and it's available for query. And in doing so, the indexer kind of interacts with upsert manager to update the upsert semantics. So upsert manager maintains some table in memory so that you know like what are the events you've seen before for that particular segment, right? And this is also pluggable. So these are the main components in the stream processing in Pinot server. Now if you look at it, this is like a mini stream processor. Like for those who are familiar with like a stream processing system, even those systems kind of do these things. So there is some amount of overlap between what a stream processing framework does for you, for the user, versus what Pinot's real-time engine is doing. So we're going to look at how Pinot kind of solves some of these problems, given that you have a very nice pluggable model, right, and a lot of similarity with the stream processing system. So let's get started with data transformations and derived data. So Pinot has a lot of transform functions, right? There's a large library of like inbuilt transform functions, but it also allows you to define custom transforms. So this is the pluggable part I was talking about. Like you could define your own transform functions that is very custom to your use case, right? You can do that by either defining it as a UDF, or you can define a Groovy function. Or you can also annotate your, if your application is in Java, you can annotate the methods with @scalar annotation, and that would automatically be available for your Pinot table. So let's take an example. So let's say we have like a table which has add ID, views, and clicks at a given timestamp, right? So this is your raw event that's coming in. Now if I put this directly into Pinot, and I want to compute like a conversion rate since a given point in time, right? Let's say I want to do average conversion rate since a given day. Then my query would look like this. So you do a select average of clicks by views, because that's my conversion rate, like how many people are clicking after viewing, that's the conversion rate. Select average clicks by view from ads where 2 epoch days, that is a function that converts the timestamp into in the order of days. So basically it ignores the more granular time, right? So then these are the two transform functions that you can use, right? This totally works and is great and is very convenient, but it's not really performant, right? There's definitely a cost every time you run that query, because every time you run that query, you're going to be converting the timestamp for every single record that you scan, and then you're also going to be computing the conversion rate. And more importantly, you won't be able to apply any kind of index on those transformation results because they are stored in a very raw format, right? So then there is no way for you to kind of improve the query performance beyond that query statement. So this is where ingestion transform comes in with Pinot. So what ingestion transform does is you can define transform configs as you see here. So I say column name day ts, and my transform function is 2 epoch days of that timestamp. Same way for hours ts. So there are two different granularities. So what happens when you define this transform function is that whenever it sees a message, it will compute these values and also store that in your Pinot table. So now this is an actually pre-materialized transform, right? That it becomes a Pinot column by itself, which means you can now apply index on this pre-materialized column. For example, I could have like different kind of range indexes applied on any of these time columns. Depends on like what your use case is, right? So when this happens, now your query goes from being this to this, where you just say select average of clicks by views from ads, where days is greater than whatever filter value. So what happened here is that the days TS, it's already materialized in your table, which means I don't have to go and during query, it doesn't have to go and convert that timestamp every time for every record. So this is an improvement, right? And because you used ingestion transforms, but you still have some more computation because you're still doing clicks by views, and that is still at a record level. So and this is still happening at query time. This is further improved by using derived columns. So derived columns in Pinot lets you compute values from other columns in the record. So you could also chain computations as you ingest. So and this is also happening during ingestion time. So everything is already in the most optimized format for you to query when it enters Pinot, right? And the other benefit is that you don't actually need to like refill your data fully and like repump in all the data. You could just update the config and reload all the segments on your servers, and it will automatically materialize even in the previously ingested data. So now your data, and this is how you do it. So you can specify a column name, conversion rate, and this is my actual function. So any valid expression here can be used as a transform function. So now this query kind of becomes like this. So I just do average conversion rate from ads based on my filter. And this is going to be much faster because I'm not doing any computation during query. I'm just looking at that average value for that given column. So this is how you can leverage derived column to kind of make your query more efficient. All right. So we dealt with some transformation and derived data. Next, let's look at complex types and nested fields. So what I mean by complex types is this kind of data. So this is basically a pull request event. So this is an open source GitHub event, right? It has a lot of fields, and some of the fields are nested. Some of them are like doubly nested. Like if you look at payload, it has pull request, and pull request has user. So this is a lot of levels of nesting. But what I'm really interested in my Pinot table itself is these fields. I just want to get the ID, pull request, the type of event, the name, some number, some timestamp, and one specific field. Now in order to do this, you could always store all these top level fields in your JSON string as a JSON string and then extract it during query time. Like you could do it like this. So you have select ID, type, and you have these JSON functions that you can apply during query time, right? So you would extract from that JSON saying repo.name or payload.number. You can also like make it multi-level. So you can say JSON extract of another JSON extract and get all the values that I want. But then again, it's the same problem. It's not optimized for your query because you're applying transform functions at query time. And in this case, it's even worse because for every record, you're going to convert the stored JSON string into an object to apply that function, right? And again, you cannot apply indexes on these fields, and you're paying the cost of storage overhead because you're storing the entire JSON string in your DB. Now we can optimize this using ingestion transforms in Pinot, and this is where the complex type config comes in. So you can specify a complex type config in your table config, and it says the delimiter is dot. What that means is that Pinot tries to flatten all the maps recursively, and it goes to infinite depth. You can also control the depth using another config called max depths, but basically it will flatten all the maps in your input data. So then in your schema, you can actually just say payload.pullRequest or repo.name or payload pull request.labels, and you don't have to worry about like how that transformation, like you don't have to do that transformation during query, right? So this is how you would modify your schema, and you do that, you get a table with this kind of data, right? So the other thing I want to point out is, like, if you look at the labels column, it is a complex type, meaning it's a collection, right? It's an array. So there are also cases where you want to kind of, you have like an array of records and you just want to flatten them, right? So if you try to flatten this, then you kind of get 2 rows after your transformation, even though the input was just one event. So you could still do that in Pinot, and you can use the field to unnest config in the complex type config to unnest your arrays. And when you do that, your schema is slightly different, but your results are that now you're able to flatten them into 2 rows. So you had one event, but you're still able to get individual records in that collection, right? So this is one of the, it's a pretty powerful feature, and it's super handy when it comes to like raw events that have like huge collections. So sometimes it's more optimized from the event generator side to produce a collection rather than individual event. So in those cases, you still want to be able to handle at this granular level, then you can just flatten it in this way. So that's what this fields to unnest offers, right? So we are able to deal with some complex type and nested fields, so I don't need my stream processing for that, right? Now let's look at data granularity. So data granularity, like I mentioned before, you could have your raw events at a very low granularity and you don't really care about it, or your use case, your analytical use case doesn't really care about it. So in this example, right, you have a product, you have a sales price, and you have a timestamp at which the sale occurred. But what we are really looking for is that the event itself is occurring in milliseconds, but as someone who's in, like, let's say sales, may only look at daily price or daily total sales of a given product, right? So you want to be able to do these computations at a different granularity than your raw event itself. And to do that, so you could do this, right? You could always do, select count star and then sum up the price column from sales, and then you're grouping by every product, and you're again using the transform function there, 2 epoch days and timestamp. Now, like we saw before, 2 epoch days runs at query time, that's one thing. But then when your application doesn't really need that level of granularity, you don't even have to pay the storage cost by storing all these events, right? So you could try to aggregate this during ingestion itself, and this is a feature that Pinot has called ingestion aggregation. So you can specify your aggregation functions that can be applied during ingestion itself. So you would say, like, okay, I want a column that says total sales, and total sales is just summing up my price, and there's a column name that's doing sales count, and that's just doing a count star. So the sum price, in the aggregate function sum of price is actually the original column's name in your raw event, right? So once you specify this, as you ingest your data, the data gets stored in this format. So now you have your timestamp at a much higher granularity, and you have also aggregated your data, right? So your sales count for, let's say, 24th October, you had 2 cars sold and 1 truck sold, and you already have your aggregate value. So when I query it, I don't really need to go and do that sum or count star. I could just do a regular sales count, total sales, and group by the filters, right? So this depends, right? Like, if your use case really wants to have flexibility to query at different granularities, then you probably wouldn't want to use it. But if you know that your use case only needs aggregated data, then you should just use this, because you're going to be saving a lot of cost and also performance penalties by just storing what data is needed for your application, right? So some of the aggregate functions that we support out of the box are these. There is sum, min, max, count, and distinct count HLL. Some caveats though is that when you're ingesting, you need to make sure that all your metric fields have an aggregate function, because if some of the metric fields don't have an aggregation function, then you will not have the 1:1 mapping, right? Or n:1 mapping. You might end up with more than one record after your aggregation. So this is the one caveat with the ingestion aggregation. All right, so we dealt with this. So Pinot is able to do all these stateless operations of like computing on the fly and applying all these transforms. Now let's look at some data semantics that is takes a little bit more of maintaining state and looking back, right? So data semantics. So let's take an example, which I think is the most direct correlation with what I mean by data semantics. Is let's say we have a MySQL DB with a lot of mutable records, right? If you have a DB, you can create a record, you can update it, you can delete it. Now, if you want to take data from a DB or a transactional data store like MySQL and dump it into an analytical store, which purely is, I mean, it only stores immutable records, right, like Pinot. Then what you're dealing with here is that you need to observe events happening on your MySQL DB. So when you create, that is an event, right? When you insert, that's an event. When you update, it's an event. So each of these events need to be translated into an actual record. So you're not going to store that entire event, right? And what this essentially is doing is it's creating multiple events for the same record key. So if you have a table with a primary key, then a record with the same primary key gets multiple events. That's what this means. So now you are only interested in like what is the latest value for that key. You don't care about what the changes came in, but what is the latest value of that key when I run the query, right? So that's what data semantics is, where you're trying to maintain some kind of state to derive the actual record value. And one common way that people do is you have like frameworks like Debezium that provide variety of connectors. So Debezium provides connectors to generate these change events from a variety of DBs like MySQL, Mongo, Oracle, and quite a few others, right? And these change events are available in real time as and when they occur. So as soon as you insert a record, it's going to create an event, and that can be pumped into Pinot. So it doesn't even have to be Debezium. It could just be a stream of updates to the same record. For example, if you imagine like how DoorDash order system works, right? You place an order, but for the same order ID, once you place it, you have different status. So you say order is placed, your order is in progress, your order is fulfilled, your order is delivered. So all these are different raw events, but they all pertain to the same record, right? So doing that is, that is also kind of in line with what you're trying to do here, very similar to change data capture. So let's look at an example on how you can do this. So if I have a MySQL database which has like some movie DB, and I want to create this record, and this is my primary key. So my ID is like 1002, and it has 3 columns, right? So as soon as this record gets created, if you were using Debezium, it would create an event like this, right? It shows you a huge payload that says like this was the value before I did this operation of create, and this is the value that happened after. So the value of the record in the source is in that after column, right? And the operation here, if you look at the bottom, it says OP, that says C, which means I just created a record, right? So this is an event, and this goes into whatever streaming system you have. And if someone goes and updates the field, like if they go and update the ranking, now it creates one more event, and that event it has the same templated format, but then now your before and after are also updated. So your before has what was the older value, and the after field has what's the current value after this event happened. So when you pump in this data into Pinot, so StarTree has a Debezium decoder for this that can actually parse only the relevant fields, just like how we saw before with the complex types and nested things. So the Debezium decoder allows you to only pick out the fields that are required and defined in your schema in the Pinot table, right? So this decoder works in hand with the upsert manager. So what happens is when this create event comes in from the stream, it gets decoded, and then during indexing, the upsert manager, when you index, you store the record in the segment, right? So you store the record as because I stored all the ID, name, and the rating. But additionally, the upsert manager now has this map saying like, okay, for this primary key, this is my current doc ID with the latest value for this record, for this key. So now when an update comes in, the same thing happens, but this time the upsert manager is like, okay, now the latest value is in doc ID 2. So you're still storing that in the segment, but your upsert manager knows what is the latest value for that particular key. So when a query comes in, it looks up the index and works hand in hand with the metadata stored by the upsert manager to actually fetch the latest value, right? So you're not looking at any of the older values. So this is kind of how you can have some amount of look back and apply some semantics on your data to be able to capture like the latest value of your events happening, right? So we are able to apply some amount of data semantics as well, right? So these are a lot of these are pretty powerful ingestion features to happen during ingestion time, right? But so does this mean stream processing is still needed? Probably yes. You still need stream processing, and you need that when during certain situations, like if you have multiple data sources, right? You typically would end up doing a lot of processing on these streams. Like you could do a stream table join, or you could do a stream and stream join. These operations are inherently like done by stream processing frameworks, and they're good at it. So this is one of the situations where you may not be able to directly inject into Pinot, and you might need that pipeline where you go through a stream processing system and then you put into Pinot. Then the other situation is where you want to repartition your data. So your source may have like thousands of partitions depending on the payload, but you might be filtering a lot of the data, and you don't want to actually store it in that many partitions on Pinot side, because if you remember, Pinot does a partition level consumption, right? So whatever number of partitions you have in your source is what ends up in your table. So if you don't want that and you really care only about a subset of it, then you would reduce your partitioning. So that's where the repartitioning happens. So to recap, it's a very pluggable architecture. You could plug in any of those real-time engine components that is suitable for your use case. And the engine provides a lot of inbuilt data processing features, like you can apply a lot of transforms during ingestions, you can derive columns, you can parse complex types, you can do filtering and flattening. You can also aggregate your data on the fly as you ingest and apply some upsert like semantics. So the takeaway that I would like to go with this talk is that if you're trying to ingest data into Pinot and you want your queries to be very optimal, get it to the most optimal form possible before you get it into the DB, and you leverage these ingestion time features to be able to get to that form faster. That way you can avoid running a whole stream processing pipeline or doing backfills with a Lambda architecture, and you could avoid all that and just do complete real time. So looking ahead, there's still more to do. We do want to improve more on the real-time engine. These are some of the features that are in progress and that are planned. So the most important one I think is like the record deletion with upsert tables. So remember we saw the data semantics example where you're dealing with create, update, and delete events. Pinot still needs to, we are still working on supporting deletes itself. So you actually remove the record from queries. So that's in progress. And once you start doing upserts, what you noticed is like all the documents, all the updates are still in your segment. So which means even though you care only about the latest value, you're still storing all the changes. So there is an effort to kind of do the compaction on these tables where you only store the latest value. So that's in progress. We also want to work on data enrichment. So data enrichment is like where you, when you get a stream of data, but you also kind of want to look up and add more fields, and that field, the data for that field comes from an external source, right? Like for example, you could have your own UDF for lookup, and you could join with an external source, like query it every time you ingest and add it to your table. But it's more efficient to do it inbuilt. So that's the lookup kind of join that data enrichment talks about. And also supporting from multiple sources, and that's quite a big change given how Pinot is architected today. But this is also one of the areas that we want to invest. The clickers. All right, that's it for me, and happy to take questions right now. Thank you.
Who has a question?
Go for it.
Did you say the transformation configs and the complex type configs could be like updated to evolve the schema on the fly? And how is that leveled back to the segments that have already been written to deep store?
Yeah. So the question is the transformation functions and complex type configs. Is it going to be able to update the schema on the fly? Is that your question, right? So you can apply. I think think there are two parts here. Some of the functions you can apply on the go, like you already created a table and you can just update your table config. And once you update the table config, there's an operation called reload that reloads all the segments, even the segments that were already ingested. So it would go and apply those transforms again on those already sealed segments per se, right? So, but there is also some category that I think you cannot. But for most of it, you should be able to just reload and it'll work. Yeah. Okay. Somebody else had a question there.
Thanks for the talk. With some of the looking ahead stuff and also the upserts,
yeah,
as the stream or the real-time engine becomes more stateful, are there thoughts to move that state to something more persistent? Because I believe upserts works in memory right now.
Right. Yeah. Yeah. So I guess the more question is like, today upsert stores all the metadata in memory, like all the servers hosted in memory. So the question is there any plans to move it off memory and kind of make it more persistent on the servers? So StarTree, so like I showed, that's actually a pluggable component, the upsert manager. So StarTree actually has a implementation that kind of uses a more persistent store like RocksDB to do that persistence. So then you can quickly scale to like more primary key volume than what you can store in memory. So it's already there, but given it's pluggable, yeah, you could build your own as well. Yeah. For joins, you mean on the query path?
Like on the ingestion path, when
Oh, you mean like multiple sources? Right now, no, at least as far as I know. But if there is a good reason, and I don't see why it cannot be used, right? Yeah. Yeah.
Hi.
Oh, I'm sorry. Go for it. I'll get you next.
So this is for UDFs.
Yeah.
Is there a capability to encrypt, to upload some UDF jars, and to encrypt certain fields or decrypt certain fields on the fly?
Yeah. So the question is for UDFs, is there a capability to have custom UDFs that can encrypt certain fields in your record? That's the question, right? Yes, that's pretty much what UDFs do. So you could have your own user-defined function, and you can make, as long as the UDF that you've defined is accessible to the runtime, you should be able to apply those and encrypt it on the fly. Yeah, you just need to make sure that your UDFs are like not long-running jobs. Yeah, just to keep that real time. So you had a question.
Sure.
Thank you.
Yeah.
So for the ingest time aggregation, is that like a view or a materialized view?
It's a materialized view.
Okay, so as you get, how often is it recomputed? Given that it's a materialized view and you have records constantly coming in.
So it's at a segment level, right?
Okay.
So as in when a record comes in, it recomputes.
As it comes in, it recomputes the
Yes.
number. So even if you have late arrival data, it will keep recomputing things as data is coming in.
Yeah, there is some support for out-of-order handling, if I remember correctly.
Okay.
Yeah.
Right. And it also works with the deep store. So
Yeah, whatever you put in
Yeah.
the segment, like adding it to the deep store is independent of what
Got
your
it.
transforms are doing.
Okay,
Right?
thank you.
Yeah. Yes, one more question.
Can the derived columns be used in the table index configuration? And is it
Yes.
respected by like segment pruning and that sort of thing?
So question is, can the derived columns be used in the index configs, right? And it'll be respected by the queries. Yes, you can. So that is a benefit of using a derived column, is that now you can index on those columns because it is actually materialized in your table. If you just use transform functions, then you're just doing everything at query time, right? Yeah.
Hey, thanks for the talk. So I have a more of an orthogonal question, which is, as we add more logic to our transformers in Pinot,
Yeah.
there's also sort of a cost of maintaining that logic, and that logic lives outside of the core, production code that lives. Is there any thought on how you could effectively manage that difference of this production code, and then there's some amount of business logic in the data set right now? And is there any thought on how we could sync it or keep it in some sort of a visible.
So you want to be able to sync your business logic that's different in your production versus your non-production use case?
Or I guess just the definition of the transformation itself. Let's say today it's an average, tomorrow it's a sum or a distinct sum. You know, the fact that that business logic now lives within the definition of the
right,
table.
yeah, so it is still tied to that specific table itself. So I think you're trying to see if you can apply the same or let's see, you don't want this one-on-one between like this is my transform functions for this table. Right now that is how it is. There is no way to share or like other than just creating one more table.
Right.
So there's no, you will end up duplicating data if that's your concern. Yeah.
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 I think we have time for one more.
Yeah. So she had one more question here.
Okay.
Is there any plan in future to be able to define certain fields as encrypted and provide the encryption at the schema configuration time itself?
Sorry, can you repeat your question? Because
so we have a dictionary of static fields, some standard fields that are encrypted all the time because they're categorized as highly confidential and PII, etc. So is there a way at the schema configuration time we could define them as encrypted? Is there any plan for something like that? Instead of writing a separate UDF and...
Oh, so inbuilt encryption functions, you mean?
Kind of, you just say, okay, this is the type and this field is encrypted.
Oh, so basically don't encrypt it, but just store it as encrypted as is.
Yes.
I'm not aware of a plan to do it, but I don't see why not. Like, it seems like another type of field that you want, right?
Yeah, but I want it at the schema configuration without having to go define and user-defined
Yeah,
function.
I'm saying you could extend it, but it just doesn't exist today.
Right, yeah, exactly. Any plans for something like that?
Not that I'm aware of it, but if there is a real use case, you can create a issue in open source and we can follow up.
Right.
Yeah.
Okay.
Yeah.
One more thing is when the data is pushed to the deep store, how do you maintain the low latency?
So even though that's a good question. So when the data is pushed to deep store, it's more for like resiliency of data, right? So the servers are still going to be hosting the
data
segments on their disk, right? So if a server goes down, and then you want to make sure a replication is on par, you bring up a new server. That server will download from the deep store, and it will still host it locally. So you're not querying to deep store every time.
Right.
Yeah.
So what about the incomplete records in the segments then? If there is a failure, then they're lost. Right?
Yeah, so what happens is in the consuming segment, these are, so what happens is only that segment will restart consumption from the beginning of that segment. So it's not like complete refill, but it's going to be pretty small, right? Because your segments are chunked pieces.
Right.
Yeah, so that chunk will be reprocessed, re-ingested.
Okay.
Yeah.
Sounds good. Thanks.
All right, that is all we have time for. Thank you, everyone, for attending, and thank you, Navina.